Good morning, all. Is it visible? Please respond.
Yes, sir, it's visible.
Okay. So in today's class, we are going to see this one more test, that is cone penetration test. Okay. Like standard penetration test, we have one more test. Okay, that is cone penetration test. We call it as a CPT. That is SPT. This is CPT. So this is the cone penetration test. So this SPT and CPT both are called some sounding methods. So sounding methods are frequently used to determine the penetration resistance and the engineering properties of the soil. The sounding methods mainly consist of cone test and the standard penetration test. Okay. So why very less people have joined? 9:30 is early to you. Visible. So the these particular tests are called the sounding methods, whether it may be standard penetration test or cone penetration test. So what is this cone penetration test? As the name suggests, there would be some cone, and what we'll do, we will apply some thrust over it and we'll try to push it, and it will give the resistance. So based on that also we can identify the soil conditions. Okay, there are correlations between the CPT cone resistance and the SPT values. So this is the cone penetration. So as the name suggests, you just look at here. This is the static. There are two types actually: static cone penetration and the dynamic cone penetration. So first, as the name suggests, this cone penetration test, also called the Dutch cone. That means Dutch government has prepared this one. That's why it is called the Dutch cone penetration. And this is the figure. Okay. So this cone is having the apex angle 60 degrees here. 60 degrees angle, and overall diameter is 35. Okay, this diameter is 35, and giving in area, total area is 10 centimeters square. Okay, for obtaining the cone resistance, the cone is pushed down. Okay, for obtaining the cone resistance, sir, good morning, sir. Sir, I am in class. May I call you after some time? 9:30 class. Huh? Okay. So this is the cone is pushed. Cone is pushed down at a steady rate of 10 mm per second. Okay, through a depth of 35 mm each time. Okay, So the cone is pushed by applying thrust or not by driving it. Okay. So what we'll do is in static cone penetration test, we will apply thrust and it will push. Actually, this nowadays automatically it will give the readings. It is connected to the computer. So when you try to push it, and it will try to give you the resistance, cone resistance. So this is famously called it as a Dutch cone. So here we'll be having sleeves, and this is of 16 diameter. This would be pressed. Okay, and what happens now? Anyway, I will show some of the videos. So this sleeve also, by using this we can collect sample also. Sometimes we can collect, it's our wish, we can collect sample also. The sleeves goes down. Okay, and cone may be retained somewhere here, and here we can get the soil. Anyway, I will show some of the videos, so that would be very interesting. So after cone resistance has been determined, the cone is withdrawn, the sleeve is pushed on the cone, and both are driven together into the soil. Okay, and the combined resistance can also be determined. That means we can determine the cone resistance here, and this sleeve resistance and friction resistance, I would say this also can be determined. The tip resistance we can determine, and we can determine the side frictions also. A modification of the Dutch cone penetration is a refined Dutch. Okay, there are so many modifications. It has got a friction sleeve of limited length above the cone point, and it is used for obtaining the point resistance of the cone and the friction resistance both. Here, if you see this one, for the use of this cone penetration, some reliable calibration is required. So this consists of the comparing the results with those obtained from the conventional test. What are those conventional tests? On undisturbed soil, we use standard penetration tests have been more commonly conducted compared to this one. We conduct this in the past, and it has good correlation studies available between the SPTN and the engineering property as we have given, and that's what it is given now. Okay, so here if you see, there are correlations given between the n value and that. The following relations holds approximately good between the point resistance of the cone and the standard penetration. That means if you know the n value, we can find out this point resistance, the cone point resistance. Understand? So for a gravelly soil, it is 800 N to 1000 N. For sands, it would be 500 N to the 600 N. For silty sand, it would be 300 N to the 400. For clay, it would be 200 N, where QC is the kilonewton per meter square resistance. Next, in the cone penetration test, we'll be having dynamic cone penetration. This is one, is second one. Okay. As the name suggests, what we'll do, we'll apply load dynamically. I mean, this is the dynamic cone penetration test. How it looks like. Anyway, I will show in the pictures. Okay. Sorry, videos. There are very good videos are available. So what are the diameter and all these things? Okay, these are the diameter, there would be hole and so on. Okay, so what we are doing here is we are finding mainly a resistance of a ground. We will try to push it, or it will be driven with a number of blows, and we'll find out the n value also. Here even the dynamic cone penetration test, so here we will apply the load. This test is conducted by driving the cone by blows of hammer, like we have done in the SPT test, number of blows. So the number of blows for driving the cone through a specified distance is measured of the dynamic cone resistance. So dynamic cone resistance are performed either by using 50 cone, okay, without bentonite slurry, or a 65 cone with a bentonite slurry. That means we use sometimes in the field bentonite slurry uh, while performing it. So IS code has given this one, okay. So driving energy is then given by a 65 kg. Here what we'll do is in the SPT 63.5, here 65 kg hammer falling through the 75 centimeter. The number of blows for every 10 centimeter penetration is recorded here. There 15 centimeter we have recorded. The number of blows required for 30 centimeter penetration is then taken as the dynamic cone resistance. If the skin resistance is eliminated, the test is conducted in a cased boreholes. Understand? If you don't need the skin resistance. So likewise, we generally find out this this kind this dynamic cone penetration when 65 cone is with bentonite slurry is used, the setup should have the arrangement for the circulating slurry, and these are some procedures. Okay, so next there are correlations between these also. So again there are correlations with the n values. Dynamic cone resistance would be 1.5 times the n for depth up to 3 meter, for depth up to 6 meter, and greater than that one. So this CBRI, Central Building Research Institute, it is there opposite to the Roorkee, IIT Roorkee, has developed some correlation based on their research and the experience for 65 diameter. So they says that it would be 1.5 n for a depth up to 4 meter and so on, and 1.75 for a depth of 4 to 9 meter and so on. So what we have seen now today is uh, the cone resistance test. That means after the SPT, this is the CPT, we call it. In the CPT, we have static cone penetration test and we have dynamic cone penetration test. Static means we apply the thrust. Dynamics means we will try to apply the number of blows. And nowadays, if you see, anyway, I have prepared so many videos for you. Okay, that I'm going to show you soon. Uh, some of the videos are very good. Unless you see videos, it would be very difficult for you to understand actually how it will work. So before going to the, CPT, first we will see the standard penetration test video. So how it looks like, how generally we conduct this SPT in the field. So first we'll see this SPT, then we'll go for the CPT. Okay, and boring and all, you can see so many videos how we can make the bore holes by using the uh, by using the standard split spoon and auger boring, wash boring, rotary boring, percussion boring, and so on. So that boring, those methods are just to make the bore holes. After making the bore holes are a pit at a certain depth, which already we have seen. After making the pit or a borehole, we'll be conducting this SPT and the CPT on a particular depth. SPT is used for finding the n values, and CPT also will be used finding the n values. If it is a dynamic or cone penetration resistance would be used, and there are correlations between these two, SPT and the CPT. So so first we'll see the SPT. Is it visible? Please respond.
Yes, sir.
Are you able to hear?
No,
Sharan,
sir.
please respond.
Sound is not there.
Sorry,
Sound is not coming.
sound is not coming. That's what you should respond. Then only. Now respond.
Yes, sir. Now it's coming.
Hello all. Now we will see how to conduct standard penetration test. It is one of the most reliable site investigation technique. So why to delay? Let's perform. Consider this as your site and here is the point where you wish to explore soil properties at a depth of 1 meter. Now make a borehole up to the desired depth. Place that tripod concentrically above your borehole. Take your gate rod and fix the sampler at bottom. Attach the hammer of 63.5 kgs and anvil to the gate rod. Make a marking of 75 cm above anvil so as to have uniform height of fall. Fix the sentry gate above the borehole as shown and place the guide rod setup through it. Keep a pulley at the top of the tripod and suspend a rope over it. Attach the hammer to one end of your rope using hook. Make 4 markings along the guide rod starting from the ground surface at an interval of 15 cm each. Now drop the hammer through 75 cm height and start penetrating the soil. Did you start counting the blows? Now you should not. Here, blows required for first 15 cm penetration is not considered as it is a seating drive. Blows required for second and third 15 cm, that is from 15 to 30 cm and from 30 to 45 cm is recorded, and that gives n value recorded. So, SPTN value is the number of blows required for 30 cm penetration after your seating drive. If number of blows are greater than 50 for a 15 cm penetration, then it is taken as ground refusal for your penetration. So don't consider that value. Your recorded gain value has number of errors and hence it needs number of corrections too. But IS code recommends 2 corrections in particular, of which first one is overburden correction. In granular soil at deeper depth, confining pressure will increase the blow count. Hence we may overestimate the strata at deeper depth. IS 2131-1981 recommends this graph for overburden correction. Apply overburden correction using this graph. Let the n value after applying correction be n naught. The next correction to be applied is dilatancy correction. If silty fine sands or fine sands are present below water table and N value after applying overburden correction is greater than 15, then the corrected N value is given as NC is equal to 15 plus half of N0 minus 15. It is to be noted here that overburden correction has to be applied first and then the dilatancy correction is done. Fine. What could we do with this SPGN value? Let's learn their applications too. Using certain standard correlations from the corrected N value, you can actually predict relative density and angle of internal friction in case of cohesionless soil. You can also predict UCS value in case of cohesive soil. And sometimes even you can predict dynamic properties too. Thank you.
Got it. Very, very useful test. Then how generally we do one more video I'll show you, okay? Because it is a very, very important test. Some people have done it here. Maybe just I'm muting it because and I'm going to explain you, okay? So this is called the split spoon sampler, okay? So it will try to split from here along like this with length. Here this is the shoes from where the soil will enter into this. From here. There is some opening here, okay? It's a hollow tube. This is called split spoon sampler. Look at that, split spoon sampler. It will be connected with rods and this is the hammer, 63.5 kg, and it will be dropped from the 75 centimeter. They will make arrangement like this, tripod kind of things, okay? And there is a ground. Now they are fixing it to the sampler. And we will mark it 15 centimeter, 15 centimeter and 15 centimeter. First 15 we will neglect it and the rest of the 30 centimeters we will count the number of blows. Now they have started, they have to lift for at the end and they have to drop it. That is one blow, okay?
Door.
It should touch, okay? Not lift. Sometimes again what we are driving it may be lifted. So just it need to touch. Yeah, that's all. That's how it would be.
तीन हो गया ना?
Yeah. It looks ground is weak. It is going down. No, they have not touched it. Okay, so they are doing some mistakes. They are not very experienced. It should just touch, yeah. At the bottom on the split, they are not touching it. So they should touch it exactly. And there is no arrangement for going into vertical. We will do some arrangement, okay? So now it looks fine. So that's how we conduct the test, okay? I hope you understood what is this SPT and all, okay? So anyway, a lot of videos are there. You can also try some good videos if it is available. There are some videos for borings also, okay? So, and there are videos for CPT test also. Just I have saved some of the videos here. Anyway, I will give all these links to you. This may be boring. No, some of the NPTEL videos I have made it for you. This you can watch later. This is about wash boring. And if possible, just let me see whether I have done some CPT. Also, you can see how it looks like. What's the time now? Let's watch this one. 10 minutes.
My objective here is to provide a simple introduction to this test method. I'll describe the measurements taken during the test and explain how those measurements are made. Finally, I'll discuss some of the applications of the CPT test. I won't be discussing details of how to analyze test data in this webcast. CPT testing is most often performed using large truck-mounted rigs. These rigs have a hydraulic jack system to raise and level the truck, and the weight of the truck is used as a reaction mass when pushing the CPT probe into the ground. For sites that can't be accessed by a large truck-mounted rig, a simple introduction.
Is it visible and audible?
Yes, sir.
To this test method. I'll describe the measurements taken during the test and explain how those measurements are made. Finally, I'll discuss some of the applications of the CPT test. I won't be discussing details of how to analyze test data in this webcast. CPT testing is most often performed using large truck-mounted rigs. These rigs have a hydraulic jack system to raise and level the truck, and the weight of the truck is used as a reaction mass when pushing the CPT probe into the ground. For sites that can't be accessed by a large truck-mounted rig, smaller track-mounted rigs are available. Very small track-mounted rigs, or rigs that fit on skid loaders, are also available for sites with very limited access. These smaller rigs are lightweight and must have an anchor system to hold them down, since the mass of the rig itself is not sufficient to provide the reaction needed to push the CPT probe into the ground. The red oval highlights one of the anchors of this particular track-mounted rig. Truck-mounted rigs are by far the most common rig used for CPT testing, and that's the rig that I'll be using to illustrate the CPT testing process in this webcast. However, the testing process is essentially the same regardless of what type of rig is used. The cone penetration test starts by locating the rig on site at the desired location. The rig is then leveled using external hydraulic jacks. The test consists of pushing an instrumented probe into the ground and measuring the forces the soil applies to the probe as it penetrates the ground. The probe is pushed into the soil using a hydraulic jack system located inside the truck. The jack system allows the probe to be pushed in at a steady rate of approximately 20 millimeters per second. As the probe is pushed into the ground, the jack is cycled up and down, and additional rods are added until the probe has reached the desired depth of investigation or until it can no longer be advanced. When the probe can no longer be pushed in, it has reached a point we call refusal. For most CPT rigs, the limiting factor on how deep the probe can be pushed is the mass of the truck against which the jack system pushes to advance the probe. Now, let's take a more detailed look at the CPT probe itself. The CPT probe consists of three separate parts: a 60-degree conical tip, which measures the end-bearing resistance to penetration, a friction sleeve, which measures the side friction, and between the cone tip and the friction sleeve is a flexible porous donut-shaped element through which pore pressure measurements are made. The rods are attached at the top of the probe and used to push the probe into the soil. The earliest CPT probes did not contain the pore pressure element and measured only tip resistance and side friction. The probe I'm showing you here is called a piezo cone because it measures pore pressure in addition to tip resistance and side friction. When we use this probe, the test is called the CEPC19 test, with the U standing for pore pressure. Today, nearly all CPT probes are piezo cones, and the test is simply referred to as the CPT or the CPT test. There are a number of different sized CPT cones as shown in this photo. All four of the cones shown here consist of a 60-degree conical tip, a friction sleeve, and a pore pressure element located just between the cone and the friction sleeve. The smallest cone shown here has a cross-sectional area of 2 square centimeters, which corresponds to a diameter of just 1.6 centimeters. Because of its small size, this cone can be used to delineate very thin soil layers. However, it has a relatively low load capacity due to its small size and is generally used only in soft to medium clays or silts. The largest cone shown here, with a cross-sectional area of 40 square centimeters, is normally used in situations where gravel is expected. The most common size cone used for typical soil testing is the 10 square centimeter cone outlined in red. Let's take a look at a cutaway section of the piezo cone and see how the measurements are made. Inside the probe, there's an inner rod that passes through the friction sleeve to the cone element. The cone is attached to the inner rod through a threaded connection. The inner rod is machined with a square shoulder partway down the shaft. The friction sleeve has a matching shoulder designed such that the friction sleeve bears on the inner rod at the shoulder. There are 2 load cells measuring vertical forces in the probe. The lower load cell measures the vertical force below the shoulder. The upper load cell measures the vertical force above the shoulder. In addition to the load cells, the probe contains a pressure transducer to measure the pore pressure. When the probe is pushed into the ground, the cone must push the soil out of the way as the probe advances. The soil imparts a vertical load on the end of the cone as it is pushed out of the way. The cone transfers this end-bearing load to the inner rod. Because the load is applied at the end of the shaft, both load cells measure this end-bearing force. The soil at the side of the probe imparts a shear force along the outside of the friction sleeve. The friction sleeve transfers this side friction to the inner rod at the shoulder, where the friction sleeve and the inner rod meet. Therefore, the friction force is measured only by the upper load cell. By simultaneously reading both the upper and lower load cells, it is possible to separate the end-bearing load, measured by both load cells, from the side friction force, which is measured only by the upper load cell. The end bearing is reported as a stress called the cone resistance or tip resistance. The symbol Q sub C is used to represent the tip resistance, and it's equal to the measured end bearing load F sub C divided by the cross-sectional area of the cone A sub C. Q sub C is normally reported in units of tons per square foot or kilograms per square centimeter. The side friction is reported as a stress called the cone side friction, or simply side friction. The symbol F sub SC is used to represent the side friction, and it is equal to the side friction force F sub S divided by the outside area of the friction sleeve A sub S. It is common to express the side friction by the friction ratio, R sub F, which is simply the side friction F sub SC divided by the tip resistance Q sub C. The friction ratio is normally presented as a percentage. The pore pressure transducer is hydraulically connected to the flexible porous element sandwiched between the cone and the friction sleeve. It measures the pore pressure directly behind the cone as the probe is pushed into the soil. The pore pressure is reported in the same units as the tip resistance and the side friction. Some CPT probes measure the pore pressure at locations other than directly behind the cone, as shown here. The symbol U sub 2 is used to designate the pore pressure measured at this location, directly behind the cone. This is by far the most common location for measuring pore water pressure. So the measurements we get from the piezo cone are tip resistance, friction ratio, and pore pressure. As you can see from this animation, these three parameters are measured continuously as the probe is pushed into the soil. Because the CPT provides a continuous profile of measurements, it is very useful in delineating different soil layers. Note that the CPT readings above the green line are notably different from those below the line. The soil above the green line produces a relatively high tip resistance, a low friction ratio, and a very low pore pressure. In contrast, the soil below the green line produces a relatively low tip resistance, a high friction ratio, and a high pore pressure. We can use the CPT measurements to classify the soil based on its behavior. This is done using the chart developed by Robertson and Campanella in 1983. As you can see, this chart has different soil classification regions based on the measured friction ratio and tip resistance. The area in the upper left-hand corner of the classification chart is an area of high tip resistance and low friction ratio. Note that the area is labeled as a region of sands and gravels. Sands and gravels have high frictional resistance but no cohesion. Therefore, when the CPT probe is pushed into sands and gravels, they produce a relatively high tip resistance as the soil shears around the tip of the probe. However, once the cone tip has pushed the sand or gravel out of the way, the soil provides very little side friction on the probe because these soils have no cohesion. For this reason, soils exhibiting high tip resistance and low friction ratio are generally sands and gravels, as the chart indicates. Conversely, clay soils generally have lower frictional resistance and provide less tip resistance during CPT testing. However, due to the significant cohesion of such soils, they stick to the side of the friction sleeve and generate a relatively high friction ratio. Therefore, if we follow a line from the area of high tip resistance and low friction ratio in the upper left-hand corner of the classification chart down and to the right to an area of low tip resistance and high friction ratio, the soil classification changes from gravel and sand to silty sand to sandy silt to silty clay and finally to clay. Although our illustration here does not have numerical values for the CPT results, we can see that the upper soil has a high tip resistance with a low friction ratio, indicating that it is a sandy soil. The lower soil layer, by contrast, is characteristic of a clayey soil with low tip resistance and a relatively high friction ratio. Furthermore, we observe a large positive jump in pore pressure as the probe enters the second layer. This is an excess pore pressure generated during shearing of the soil as it passes around the cone. Because of this positive shear-induced excess pore pressure, we can deduce that the lower soil layer is probably a normally consolidated soil. It is important to note that this classification process is known as soil behavior type classification. We call it behavior type classification because it depends on the soil's behavior during SPT testing, not on the physical properties of grain size distribution and Atterberg limits used in a traditional unified soil classification system. In order to have a definitive classification of these soils according to the unified soil classification system, we would have to take samples and perform the proper lab test to determine grain size distribution and Atterberg limits. Another common variant of the CPT probe is the seismic cone. Like the piezo cone, this CPT probe measures tip resistance, side friction, and pore pressure. It is designated SCPTU, with the S standing for seismic. This probe contains a 3-axis geophone in addition to the load cells and pore pressure transducer in the piezo cone. The geophone allows the probe to detect seismic waves. Using the geophone and a shear wave source located at the ground surface, we can determine the shear wave velocity of the soil as a function of depth. The shear wave velocity is a particularly important variable in determining liquefaction potential for cohesionless soils. To make shear wave measurements, the CPT probe is pushed into the soil and tip resistance, side friction, and pore pressure measurements made, just as we've already described. However, at intervals where we want to measure the shear wave velocity, the probe is stopped. While the probe is stopped, a shear wave is generated at the ground surface. The shear wave source can be as simple as using a mallet to hit one of the truck supports, though it's very common today to use an automated shear wave generator, which employs a solenoid attached permanently to the truck supports. The shear wave generated by the source propagates.
So this one is very advanced one, okay. So when we do MTech in geotechnical engineering, like I have done it, okay. So there we'll study this seismic cone penetration test and shear wave velocities, where when you study about the earthquake kind of one, okay. So hope you understood. There may be some truck also in the foreign country, they use it, and we can get it the exact graphs in the computer. So with that, you just I'm posting this link to your this one. Anyway, all the links I will give you anyway, so you can see afterwards. These links I will give you soon. Just I'm working on that, which are the good videos where I can give some of the. With that, we'll stop today. Then we'll meet on Monday. So shall we stop today? So please, Sharon, please respond.
Yes, sir.
Yeah, okay. So we'll stop today. We'll meet, I think, on Monday only. So wish you all the best, and please start reading it. SPT, CPT. So these are the very important tests if you want to write any competitive exams. Without